Welcome back to this series on topology. In today's video, we'll be finishing up our look at connectedness by considering components and path components. You can find the playlist containing all the videos in this series by clicking on the info thing that should appear right now. Also, if you enjoy these videos, please consider giving them a like so that other people can find them more easily. With that, let's dive straight into the first definition, which is that of a component of a topological space. For this, we suppose that X is some topological space, and then we say that a component of X is a maximal, non-empty, connected subset of that space X. Let me explain all of these adjectives in turn. So non-empty just means that this component should contain at least one point. We already know what connected means. So connected means that you can't decompose your subset into two non-empty open disjoint subsets. So that's the notion of connectedness we saw 2 videos ago. And finally, maximal needs to be understood in terms of inclusion. So a maximal non-empty connected subset means that it's a non-empty connected subset that is not properly contained in any other larger connected subset of X. All right, so to make it clear what this definition is trying to say, let me kind of sketch out what these components are visually. So suppose we have some space X, which consists of some different parts which are each connected. So these blue parts here are connected subsets of X. And now the components of X are the maximal connected subsets. So they're basically the largest parts of X that are still connected, and we can decompose X into these connected parts. So in our example here, X would have 3 components. So this one here on the left would be one component, this would be one component, and this here would be one component. So it should be clear from the picture that each of these components is non-empty and connected. Now, why do we need this maximality condition? Well, suppose we have some smaller subset here, this orange one. This one too is non-empty and connected, but it's not maximal because it's contained properly in this larger blue subset. And basically this orange subset doesn't really look like a connected part of X. So we would not consider this as a component. So the components are really the largest connected parts we can divide X into. Okay, to reinforce this definition, let me give some examples. So the first example is that of the real line without the origin. So we can draw as follows, just a line missing, well, a point. And so this line would extend out infinitely in both directions. Okay, so what are the components of this space? Well, we saw in a previous video that the real line without the origin is not connected. Why? Well, we can divide it up into the negative real numbers and the positive real numbers, and both of those sets are non-empty and open and disjoint as well, so they disconnect the space. However, those two open sets also form the components of the space, so they're the maximal non-empty connected subsets of the space. So one of them is the negative numbers, which I've drawn in orange, and the other component is the positive real numbers, which I'm drawing here in red. So the real line without the origin has 2 components, namely the negative real numbers and the positive real numbers. Moving on, our next example is the disjoint union of 2 disks in the plane. So this space basically just looks like, well, 2 circles that don't intersect. And in this case, we're thinking about this space endowed with the subspace topology inherited from the plane. Again, this space is not connected because, well, both of these disks are individually open in the subspace topology, so they disconnect the space. And in fact, these 2 disks are also the 2 components of this space. So the one I'm surrounding in blue, that's one component, and the one I'm surrounding in orange, that's another component of this space. So again, this space has 2 components, each of which is a disk. Okay, and now our final example is that of the rational numbers considered as a subspace of the real numbers. One way to draw this is to think of the real numbers as the real line, and then, well, the rational numbers are all the points that are rational in the real line, I mean, there are infinitely many of them, and they're dense in the real line, but there's basically kind of gaps between them. For example, square root of 2 is not a rational number, so we would have a gap where square root of 2 occurs. So we can basically think of Q sub r as this dense set of points in the real line. We saw in the video on connectedness that the rationals as a subset of the reals aren't connected. This is essentially because we have real numbers. So whenever we have a real number, say square root 2, we can draw sort of a division line in the real line. So here would be some real number, for example, square root 2. And now we can consider all the rational numbers that are strictly smaller than square root 2 and all the rational numbers that are strictly greater than square root 2. So this is similar to how we disconnected the real line without the origin. So we basically intersect the rational numbers with two half-open intervals. One half-open interval we're intersecting them with is the one here on the left. And then there's also a second one on the right. And because these half-open intervals are open subsets of the real line, their intersection with the rational numbers is going to be open in the subspace topology. So these are two non-empty disjoint open subsets whose union is the entire space. And hence, these intersections of these half-open intervals with rational numbers disconnect the rational numbers. So this shows that the rational numbers aren't connected, but in fact, our choice of square root 2 as sort of this point of disconnection was more or less arbitrary. We could have chosen any irrational number, and this leads to the argument that, in fact, the rational numbers viewed as a subspace of the real line have infinitely many components, where each component is just a single rational number. Why is this? Well, suppose that we have two rational numbers, p and q, which supposedly lie in the same component. So here I've kind of zoomed in on the number line. Okay, so we suppose that these are part of the same component. Now, by properties of the rational numbers sitting inside the reals, there always exists an irrational number that lies between any two rational numbers. So there is some irrational number r that lies strictly between p and q, and now basically we can do the same trick we did before and consider these intersections with these half-open intervals. So we consider all the rational numbers strictly smaller than r and all the rational numbers strictly greater than r. And these are again two open subsets whose union is the entire set of rational numbers. And they're disjoint and open. Well, therefore, these two sets disconnect the rational numbers as a subspace of R. And well, they also disconnect P from Q. In particular, this means that this supposed component, which contains both P and Q, is actually not connected. And this is a contradiction. So what this argument shows is that no two rational numbers can lie in the same connected subset in this space. And this immediately implies that, well, maximal non-empty connected subsets can't have more than one point in them. On the other hand, it's also fairly easy to convince yourself that singleton sets have to be connected, basically because you can't write them as a disjoint union of two non-empty sets. So, in fact, the singletons in this subspace Q sub the real lines are connected, but any set that's larger than a singleton, so has more points than one, is no longer connected. And this makes the singleton sets the maximal non-empty connected subsets of the space, and therefore this space of rational numbers here has infinitely many components, each being a singleton containing a rational number. All right, so I've already alluded to the idea when I gave the definition of components that they sort of divide our space into connected parts. And the way to make this formal is to say that the components of our space X form a partition of that space. Recall that a partition of a set is a family of subsets that covers the set and where the individual subsets are disjoint from one another. So let's call this family P alpha. So this is a family of sets P alpha, where each of the sets P alpha is a subset of the space X. Moreover, they should cover the space, so the union of these P alphas is supposed to be X. And finally, all of the P alphas are supposed to be disjoint from one another. So P alpha intersect P beta is the empty set when alpha is not equal to beta. Thus, intuitively, a partition is just a way of dividing up your space X into disjoint parts. And now the claim of this proposition is that, in fact, the components of X are doing precisely that. Okay, so let's give a proof of this. So the first 2 points I've written down here for the definition of a partition are pretty much immediate. So the components of X are subsets of the space X, and, well, we just gather them together as a family. So the only 2 things we need to check is that, indeed, the components, if we union them together, they form the entire space, and also that different components are disjoint from one another. Okay, so the first thing we'll prove is that the union of the components C alpha are actually equal to the space X. So there's 2 inclusions we need to show, but one of them is obvious because, well, every C alpha is a subset of X. We have that the union of these C alphas is also going to be a subset of X. For the other direction, we're going to take some arbitrary point small x in our space, and now we want to show that there exists some component that contains this point small x. The way we're going to do this is we're going to consider the union over all subsets that are connected and contain the point small x. So we consider the union over all subsets S where this element X is contained in S, and moreover S is connected. Now, by a result we saw in the video on connectedness, namely the one that said that whenever we have a family of connected sets that share a point in common, then the resulting union of those sets is also connected. So this result implies that the union we have here, since they all share X in common and they're connected, means that this union is connected. Also, it's clear that this union is non-empty because each of the subsets in the union contain the point X. So certainly the union also contains X. And finally, this union is also a maximal connected non-empty subset. Why is this? Well, suppose that we have some strictly larger set L that contains this union here. So we're assuming that L is also connected and non-empty and is strictly larger than this union. So this would be a counterexample to the maximality of this union. Well, because X is an element of the union across all these S's, it means that X also lies in L. Therefore, this set L, which by assumption is connected, also contains X, and therefore this L here is actually one of the subsets S's we're unioning over in this union, since it satisfies both of these conditions. Hence, L is actually contained in this union, meaning that L is a subset of this union, and this contradicts the fact that we've assumed that the union is strictly contained in L. So maybe to give that argument again, so we assume that this union is not maximal. This would mean that there exists some connected set L which is strictly larger than the union. However, because X is contained in this union by assumption, and this union is a subset of L, it means that X has to also be contained in L, which by assumption is connected. But this means that L satisfies these two hypotheses here on the subsets we're unioning over. So L is actually one of the subsets S that occurs in this union, and therefore L is actually a subset of this union, and this is a contradiction to the fact that we've assumed that the union is strictly contained within L, and this contradiction proves the maximality of this union. Okay, so we started with a point X in our space, and we've now found a maximal non-empty connected subset, namely this union here, that contains that point. These conditions here basically just mean that this union is a component. And so we found a component that contains our point X, and this shows that X is contained in the union across all of these components of X. So this concludes the part of the proof where we show that the union of all components is equal to the entire space. Next, we'll show that distinct components need to be disjoint. So we suppose that C alpha and C beta are not disjoint. So their intersection is non-empty. Well, then there exists some point P in their intersection. Well, then this implies that their union is connected. Again, by the proposition we saw in the video on connectedness, that whenever you have two connected spaces that share a point in common, their union will also be connected. So the way we're going to use maximality here is as follows. So we know that C alpha is a subset of this union C alpha, C beta, and this union here is connected and non-empty. And now by maximality, we know that C alpha can't be a proper subset of this union, because otherwise C alpha would not be a maximal connected non-empty subset. So we must have that C alpha is actually equal to this union, otherwise we would violate this assumption that C alpha is maximal. And now the exact same argument works with C beta, because C beta is also a component and hence maximal. C beta is also a subset of the union here, and therefore similarly we have that this union must equal C beta. So what we've shown now is that whenever two components have a non-empty intersection, then actually they must be equal. So this shows that distinct components are disjoint. And with that, we've proved the two things we need to show in order to show that the components of X form a partition of the space. And the upshot of this proposition is basically that this picture of thinking of X as being divided into different connected parts by its components is correct. Next, we'll look at some properties of components of a space. So the first property says that every component of a space X is closed in the space. While the second property says that any non-empty connected subset of X is contained inside a single component. Both of these properties follow fairly easily from properties of connectedness we saw in a previous video. So for the first part, we need to show that every component is closed. So we let C be a component of X. Now, in the video on connectedness, we saw that whenever we have some connected space, then its closure is still connected. And the way to prove that was to show that whenever a space has a dense connected subset, then the entire space needs to be connected. And then use the fact that any space is dense within its closure. However, for now we're just using this fact. So because C is a component, it's connected. So its closure is also connected. So we know that its closure is connected. Now, since C is a subset of its closure, and also C is supposedly a maximal connected non-empty subset, it means that C must equal its closure. This is again by the same maximality argument we saw in the previous proof. So it's not possible for C to be a proper subset of its closure because otherwise we would contradict maximality, therefore C has to equal its closure. But we know that the closure of any set is closed, and because C is equal to its closure, it means that C is closed. So that proves part A of this proposition. Part B is kind of similar to what we proved when we showed that distinct components are disjoint. So for this, we suppose that we have some subset, let's call it A, which is contained in the space X, and this is supposed to be connected. And now we need to show that it is contained within a single component. Also, we have this hypothesis that A is non-empty, because, well, otherwise, if it were the empty set, then it would be a subset of any component, so then this wouldn't hold. But because A is non-empty, it has a point that must be in some component, because the components partition the space. So we let small a be an element of A. Well, then small a lies in some component C of our space. This is because the components of X partition the space, so every point in X lies in some component. Now we basically use the same argument we did before, because now A, the subset A, and the component C share this point small a in common, and both are connected. We know that their union also is connected by the proposition on connectedness we used previously. Okay, so A union C is connected, but, well, we know that C is contained in A union C, and this implies that C equals A union C by maximality. This is again the same maximality argument as we've used many times now. And, well, if C is equal to the union of A with C, this means that A has to be a subset of C. So this shows that this arbitrary connected non-empty subset A we've chosen is contained in some component C, so it's contained entirely within that single component, and moreover it can't be contained in any other component because distinct components are disjoint by the fact that they partition our space. Okay, so that proves these two properties of components. Recall that in the previous videos, we saw this notion of connectedness, which means that you can't divide your space up into two disjoint non-empty open subsets. But then we also saw in the next video a notion of path-connectedness, which is sort of a different idea where we say that a space is path-connected if you can join any 2 points in the space by a path. Now, our definition of a component of a space was based on this notion of connectedness, but we can make a similar definition by using the idea of path-connectedness instead. So this is what's happening here. A path component of X is just a maximal non-empty path-connected subset of our space. So it's exactly the same definition as for a component, just that we've replaced connected with path-connected, and we call these new objects path components. Now, if you watched the videos on connectedness and path-connectedness, you will have seen that basically the same properties that we can prove for connectedness also hold for path connectedness. So it's perhaps unsurprising that the same properties that hold for components of a space also hold for path components. In particular, we have the following three properties. First of all, the path components of a space partition the space, and this is proved exactly in the same way we did for components. Secondly, we have that each path component is contained in a single component. So this is a relationship between path components and components. And moreover, each component of a space is a disjoint union of path components. So this is something that's a bit new because it describes the relationship between path components and components. However, this result follows easily from the fact that path connectivity implies connectivity. So in particular, every path component also is a connected subset of a space. And therefore, by what we've seen previously in the previous proposition, therefore every path component being connected has to be contained in a single component. So that's just a reiteration of what we just proved a few minutes ago. And then the second part here says that each component is actually the disjoint union of path components. But this basically follows immediately from the fact that path components partition our entire space X, and the fact that every path component is contained in a single component. So the way to think about path components is that they're somehow a finer partition of our space than the components, and this follows from the fact that path connectivity is a stronger property than connectivity. And the final property C for path components here says that any non-empty path connected subset is contained in a single path component. That's exactly analogous to the previous property we proved for components. So I'm not going to prove any of these because, as I said, the proofs are exactly the same as for components. Maybe just for B, the picture we should have in mind is that if our space X is composed of, say, these blue components here, then basically the path components are going to be a finer partition on our space. So maybe this entire component here in blue is also a path component. I'll draw the path components in orange, but it's possible, say, that this blue connected subset here actually consists of two maximally path connected subsets. So it's possible that this blue component here is not itself path connected, but consists of smaller path components. Maybe this one here also consists of several path components. So this way of viewing our space as being partitioned into components or path components, and the path components possibly being sort of a finer partition, this begs the question of, well, what's exactly the relationship between these path components and the components? And that's something we'll look at in more detail next. For this, we'll need the following definition, which perhaps looks a bit complicated at first, and it's that of local connectivity and local path connectivity. It goes as follows. A space X is said to be locally connected if it admits a basis of connected open subsets. And similarly, we say that a space X is locally path connected if it admits a basis of path connected open subsets. So this is perhaps not very transparent. So another way of phrasing this definition is saying that a space is locally connected if for any point P in that space and any open neighborhood of that point P, there exists some connected open set that is both contained within the neighborhood and also contains the point P. This description is more explicit, but it's also a bit more convoluted. So I'll draw what it means. So we take some point P in our space X and some arbitrary neighborhood surrounding P. So this is some open set that contains P, and it could be fairly complicated. Now our space is locally connected if, regardless of what point and neighborhood we chose, we can find some connected open set that contains P. So that would be this red set here. And the same thing goes for local path connectedness. So being locally path connected means that regardless what point in your space you choose and what neighborhood you choose around that point, you can find a path connected open set containing that point that is also contained within the neighborhood you chose. So as you can see, this definition is a bit technical, and it's maybe not the most important definition that you need to memorize. However, it will be important for proving certain properties about the relationship between path connectedness and connectedness, which will be very important later on. To illustrate the definition, let's give some examples. So the first example is that of Rn, which happens to be both locally connected and locally path connected. One way to see this is to use this first definition up here we stated, which is saying that being locally connected means that you can have a basis of connected open subsets. And well, the open balls in Rn are connected open subsets, and they form a basis of Rn. So this immediately shows that Rn is locally connected. Now these open balls are also path connected, so this also shows that Rn is locally path connected. To illustrate the second version of the definition, maybe let's just pick some arbitrary point x in Rn. And now if we choose some arbitrary neighborhood surrounding this point, so that's some open set in Rn, then we know that regardless which point we choose in this open set, we can find some small open ball that contains that point and is still contained within the open set. In particular, if we choose the point x here, we can find some small open ball containing x, and that is still contained within the blue neighborhood. And as I said before, open balls are both path connected and connected, so this satisfies the second version of the definition for connectedness and also for path connectedness. Another thing we can note is that because path connectedness implies connectedness, we can see that local path connectedness also implies local connectedness. A more or less direct consequence of the fact that Rn is locally connected and locally path connected is that any topological manifold is also locally connected and locally path connected. Recall that a topological manifold is a topological space that is Hausdorff, second countable, and locally Euclidean of some fixed dimension. For this part, the second countability and Hausdorff properties won't be important. What's important is that a topological manifold is locally Euclidean of some fixed dimension. And what this means is that for any point in the manifold, we can find some neighborhood around that point that is homeomorphic to an open set in Rn. So intuitively, locally, a topological manifold looks just like Rn for some fixed dimension n. And because of the local nature of this definition we've just given, it means that these local properties transfer to topological manifolds. So to see this, suppose we have our topological manifold M here, and we choose some arbitrary point P, and now we choose some arbitrary neighborhood around P. Now, because this topological manifold is locally Euclidean, it means that there exists some other neighborhood around P, which I'll draw in orange, and a homeomorphism from that orange neighborhood, phi, to some open set in Rn. Now, under this homeomorphism, our point P will be mapped to the point phi of P. And moreover, the intersection of the orange set with our red neighborhood we chose arbitrarily around P, this is still open and will also be mapped to some open subset in Rn. And well, now by the fact that Rn is locally connected and locally path connected, we can find a path connected open subset containing this point phi of P. And if we pull this subset back along the homeomorphism, this will give us a path-connected open subset that contains the point P and is also contained within our red neighborhood we chose to begin with. The reason this works is because homeomorphisms basically preserve all of these topological properties like openness, connectedness, and path-connectedness. Another way to think about this would be to think in terms of bases and to construct a basis for our manifold based on the pre-images of the open balls in Rn under these homeomorphisms phi that define the local Euclidean structure. The last example is of a space that is not locally connected, namely the rationals considered as a subspace of the reals. And the reason for this is similar to the argument we presented when we showed that the rationals as a subspace have infinitely many components. So suppose we take some point P, so this is a rational number, and now we take some arbitrary open set containing P. So this will be an intersection of an open set of the real line with the rational numbers. So that's what open sets of the subspace topology are. Now, in order to show that Q is locally connected, we would have to be able to find some connected open set that contains P and is also contained in this orange open set. Now, the problem is that any open set that contains P will have to contain some second rational number that is not P. So any open set we choose, regardless how small, will be the intersection of some open set of the real line with the rational numbers. And we know that for open sets of the real line, for any point we can always find a small neighborhood around that point, so a small open interval that is contained within that open set and also contains the point. So in particular, any open set we choose will have to contain a very small interval around P that is still contained within that open set. And because the rationals are dense within the reals, that small interval will also contain some second rational number Q, which is distinct from P. And well, we saw in the previous example at the beginning of this video that whenever we have a subset that contains two distinct rational numbers, this subset cannot be connected. And so this shows that there can't be any open connected set that contains P that is contained within this open neighborhood. So this shows that the rationals considered a subspace of the reals are not locally connected. Based on the nomenclature, you might suspect that being connected should imply being locally connected, but in fact this is not the case. One counterexample to this is, again, the famous topologist's sine curve we saw in the video on connectivity. So recall that the topologist's sine curve was the union of two spaces, one of which was the interval going from -1 to 1. And then also we had the graph of sine 1 over x, so that somehow oscillates and then continues oscillating faster and faster and asymptotically approaches this blue line here. And the topologist's sine curve is the space defined as the union of, well, this interval from -1 to 1, the blue one, and this graph, the orange line, seen as a subspace of the plane. The reason we encountered this space before as a counterexample is because it's an example of a space that is connected but not path-connected. So this topologist's sine curve is connected. To see that the topologist's sine curve is connected, we can argue as follows. Suppose we had some disconnection of this space, so that would be two open, non-empty, disjoint subsets whose union is the entire space. Well, because this interval from 1 to -1 is connected, it must be contained entirely within one of the disconnecting subsets. And in fact, because this subset is open in the subspace topology of the real line, it has to contain a bit more than just this line. So for any point here on this line, there has to be, a small ball that is still contained within this disconnecting subset. And this means automatically that some part of this orange curve also has to be contained within this green disconnecting subset. And now, because the curve, this orange curve, is by itself connected, it means that in fact the entire space here has to be contained in one of the disconnecting subsets, meaning that the other one needs to be necessarily empty, and so we didn't actually have a proper disconnection of the space to start with. Okay, so that's a sketch of the argument why this space is connected. And now I'm claiming that apart from not being path connected, this space is also not locally connected. To see why this space is not locally connected, I'll take some point lying on this blue interval and some open neighborhood around it. So I'll just take some ball that doesn't contain the entire space. Now if we zoom in on this situation here, we have on the one hand this line that's part of the interval. We have our point P. We have our ball surrounding P. And well, now this sine 1 over x, this will intersect this ball repeatedly, and it sort of always gets finer as it approaches the blue interval. Now, in order to show local connectivity, I would have to be able to find some open set containing P that is contained within the red set, and this open set has to, in addition, be connected. And maybe now you can see what the problem is, because if I choose some smaller open set that still contains P, and I zoom in here, the situation is basically the same situation we started with. So I have P here, and well, this smaller open set surrounds P, but the sine 1 over x is still kind of doing this thing where it always gets closer to the line. Now from the picture it's pretty clear that, well, this blue set is not connected because it consists of this, which is essentially a disjoint union of these orange lines. And if you wanted to be more formal about it, you could, choose a small open set that just contains one of the lines, and then choose another one which contains the rest of them. And well, these are intersections of open sets of the plane with this subset here, and they're disjoint because there's some space between the lines. They're non-empty, and their union is the entire subset, so this is a disconnection of this set. And basically we can always find such a disconnection regardless of how small we choose this open set around P, because in any open set around P, sine 1 over x will look like a disjoint union of lines. So there's always some amount of space between these individual oscillations. Regardless how small you choose the neighborhood, you can always zoom in more and you'll find some space which you can use to separate these lines from one another. So one way to think about this is that if we take sort of a cut out of the sine 1 over x, it looks like this disjoint union of lines. So locally it's not connected, but globally, because the curve actually sort of oscillates up and down, globally it's connected, but it's not locally connected because, well, if you don't include these bends here up at the top, then you just get sort of a disjoint union of lines. All right, so that shows that connected spaces aren't necessarily locally connected, which is maybe something you might intuitively assume. Next, we'll show some properties for locally connected spaces. The first of one being is that every open subset of a locally connected space X is again locally connected. This essentially says that being locally connected is a local property because it's inherited down to open subsets. Now the second property says that every component of X is open if X is a locally connected space. We've seen that components of a topological space are always closed. However, when that space is in addition locally connected, then components also become open. Okay, so let's prove these two properties. For the first one, since X is locally connected, it has a basis of connected open subsets. So we let B be a basis of connected open subsets. Okay, now we let U be some open subset of X. Now, in order to show that U is locally connected, we need to find a basis of connected open subsets of the subspace U. For this, we denote by B sub U. So this will be the set of all basis elements B in the basis such that B is contained in this open set U. So this will be sort of a subset of the basis consisting of all basis sets contained in the open set U. So the claim is now that this B sub U is a basis for U. And well, because the original basis consisted of connected open subsets, this B sub U will also consist of connected open subsets. So all we have to show is that B sub U is indeed a basis for U. So we suppose that V is some subset of U which is open. Now, in order to show that this B sub U is a basis, we have to be able to express V as a union of basis elements. Well, okay, since this original basis B is a basis, we know that we can express V as a union of elements in V. So V is some union of some B alphas where the B alphas are elements of this original basis B. However, since V is a subset of U, every one of these B alphas also has to be contained in U, otherwise we would get something that's bigger than U. So since V is a subset of U, and moreover, we know that each of the B alphas has to be contained in V, because V is the union of all of these B alphas. So this implies that all B alphas are actually elements of the restricted basis B sub U. Therefore, this restricted basis B sub U is actually a basis, and it consists of connected open subsets because the original basis did, and so this proves the first part of this proposition. For the second part, we basically use the characterization of open subsets in terms of finding neighborhoods around points which still lie within the subset. So we let C be a component of X. Okay, so now we let P be some point in C and consider X to be, well, a neighborhood of P. So we know that the entire space X is open, so in particular it's going to be a neighborhood of P. Then by the local connectivity of X, there is going to be some open connected set that contains P. So then P is contained in some U which is open and connected. And we saw previously that any connected set has to be contained entirely within one component. So U has to be contained in C because P is contained in C. And this shows that C is open. Why is this? Well, we've chosen an arbitrary point in our set C, and we found some open neighborhood around that point that is entirely contained within that subset, and this is one of the ways we can show that a subset is open. So essentially, local connectivity guarantees that around each point we can find some open connected neighborhood, because we can always choose this arbitrary neighborhood to be the entire space X, and because, well, such a connected neighborhood has to lie entirely within a component, this means that components are open in locally connected spaces. Okay, so that proves both of these properties. And in fact, the property that components in locally connected spaces are both open and closed will be very important in what is to come. Now, before going into that part, which will conclude the video, I'll say that Essentially, the same properties also hold for local path-connected spaces. So if X is a locally path-connected space, then, well, we have that open subsets of that space are again locally path-connected, and also that every path component of the space is open. And these two properties B and C are proved exactly in the same way as we did for components. Another thing I've written down here is A, is that if X is locally path-connected, then it's also locally connected. That's something I remarked before. This immediately follows from the fact that path connectivity implies connectivity. So if you have a basis of path-connected subsets, then, well, these subsets are automatically connected, meaning that your space is also going to be locally connected. So if you want, you can prove these things for yourself, but as I said, the proofs are exactly the same as for the locally connected case. This brings us to the reason why we're interested in locally path-connected spaces in the first place, which is that in locally path-connected spaces, the notions of connectivity and path connectivity coincide. This is something I alluded to before in previous videos, where I said that in nice spaces like topological manifolds, we don't really have to distinguish between being connected and being path connected. And well, the way to show that this is true has to proceed via this definition of the local versions of these properties, namely local path connectivity. Okay, so what is this proposition saying? So part D is saying that if X is a locally path-connected space, then the path components of X are the same as its components. So we saw previously that if we have some arbitrary space, the components of that space partition that space, and the path components also partition the space, potentially in a finer way. So every component of the space is the disjoint union of some path components. However, this proposition here is saying that if the space is itself locally path-connected, then the path components and the components of the space coincide. And in particular, this will imply that in a locally path-connected space, the space is connected precisely when it is path-connected. And again, this is important because we have these two notions of connectivity, connectedness, and path-connectedness, and in general, path-connectedness is much easier to work with. And this proposition is saying that if your space is locally path-connected, then you don't have to care about the differences between connectivity and path-connectedness. You can just go between them at will. Okay, so let's give a proof of this. Part D will use the fact that we've shown that in locally path-connected spaces, the path components are both open and closed, and similarly in connected spaces, the components are both open and closed. Okay, so to prove this, we take some arbitrary point P in our locally path-connected space X. And now we know that X is both partitioned into components and also into path components. So this means in particular that P will be contained in some unique component and also in some unique path component. So we denote by C the component containing P, and by P the path component containing P. Okay, so maybe let's draw a picture of this. So we have our point P, then P is contained on the one hand inside some component C, and also on the other hand inside some path component P. Now we know that the path component is path connected, so in particular it's going to be connected. And we also know that any connected subset has to be entirely contained within a single component. So the way I've drawn this picture here can't actually be the case. P has to be a subset of C. So let's redraw that in the correct way. We also know this because, well, components are the disjoint union of path components. So P has to be a subset of C. So we have P being a subset of C, for example, because P is connected and so must be contained within the component C. However, we know that in a locally path-connected space, the path components are both open and closed. So we saw that in any space, components and path components are closed, but if the space is locally path-connected, then the path components are also open. Now, if you think back to the video on connectedness, we saw one proposition there which said that if you have a subset of a connected space which is both open and closed, then it must be the entire space. And well, this is exactly what we're going to use now. Because P is both open and closed and it's contained in some connected set, it must be the entire connected set. The way to see this from scratch is to assume that P is not the entire set C and to provide a disconnection of C. So how are we going to construct the disconnection? Well, we already know that P is open and it's non-empty because it contains this point small p. So that's going to be one of our disconnecting sets. And the second one will be the complement of P. So the complement of P is this in yellow. And now because P is closed, this complement will be open. To do this more formally, we define Q to be the intersection of the complement of P, so that's X without P, intersected with C. So that's this yellow set. I mean, there might be some other stuff going on around outside of C, but we're just interested in the intersection of the complement of P with C. And because P is closed, we know that this complement here is open. And moreover, we also know that C is open. Why is this? Well, C is a component of X, and we saw that components of locally connected spaces are open, and we know that X is locally path-connected, and we also know that being locally path-connected implies being locally connected. So this is open because X is locally connected. Therefore, Q is open. Okay, so now suppose, for the sake of contradiction, that P is properly contained within C. Well, then there would be some point small q outside of P. And well, in that case, this set Q here would be non-empty. And then P and Q would disconnect C. Why is this? Well, P is open and Q is open. Both of them are non-empty if we assume that P is properly contained within C, since P contains the point small p and Q contains the point small q. And finally, they're disjoint because Q is the intersection of the complement of P with something, and so it can't share any points in common with P. So if P is a proper subset of the component C, then P and Q disconnect the component C, which is a contradiction, since, well, components are connected. This contradiction means that our assumption that P is properly contained in C must be false. So in fact, the path component P has to be equal to the component C. And now we've shown that for any point in our space, the component it's contained in is equal to the path component it's contained in. And now since, well, every component and path component contain some point, this also shows that the path components of the space have to be the same as the components of the space. Okay, so we've shown that in the case where X is a locally path-connected space, its path components are the same as its components, and the essential tool for proving this was the fact that path components are both open and closed in locally path-connected spaces, which means that, well, if you have a path component contained in some connected component, then it has to be equal to that connected component. Okay, And now from this, it immediately follows that connectivity is equivalent to path connectedness in the case where X is a locally path-connected space. Why is this? Well, suppose that X is connected. Well, this means essentially just that X has a single component. And well, if X is path-connected, this means that X has a single path component. And now, because we know that components are the same as path components whenever X is locally path-connected, it means that X will have a single component if and only if it has a single path component. And so this shows that X is connected if and only if X is path-connected, provided that X is a locally path-connected space. Okay, so all of this video was fairly technical, but the main take-home message is that whenever your space is locally path-connected, then the notions of connectivity and path connectivity coincide. And moreover, these tools of using path components and components can be very useful in arguments in general. So in particular, we saw that topological manifolds are locally path-connected. So this proposition shows that in the case of topological manifolds, connectedness is the same as path connectedness, and this is very helpful because, again, working with path connectedness is usually easier than working with connectedness. Okay, with that I'm done with what I wanted to say in this video, and in general with what I wanted to say about connectedness and path connectedness. In the next video, we'll be looking at a new concept, namely that of compactness, which turns up all over the place and is even more important than connectivity.